In this video, we're going to focus on the topics that you've learned in the first semester of your college general chemistry course. Now, this information can still help you if you're taking IB or AP chemistry in high school. It covers the first half of what you learn. So it covers stoichiometry, percent yield, empirical formulas, how to find the limiting reactant, how to convert from grams to moles to atoms or molecules. It also covers dilution problems, balancing equations, how to find the oxidation numbers, how to identify if it's an oxidized or a reducing agent. We're also going to talk about gas laws, PV equal nRT. We're going to go over vapor pressure, partial pressure, Graham's law of diffusion, mole fraction, and the kinetic molecular theory. We're also going to talk about solution stoichiometry, and we're going to go over molarity, molality, mass percent, Lewis structures, molecular geometry, how to find the enthalpy of the reaction using bond association energy or heat of formation, and even Hess's law. We're going to talk about all of that. We're going to go over intermolecular forces, boiling point vapor pressure, like boiling point elevation, freezing point depression, osmotic pressure. Basically, almost everything you've learned in the first semester of your chemistry course. So let's go ahead and begin. Number 1. How many protons, electrons, and neutrons are found in the ion shown below? An ion is a particle that has an unequal number of protons and electrons. In this particular ion, we have a charge of +3, which means that there are 3 more protons than electrons. An atom is electrically neutral. In an atom, you have an equal number of protons and electrons. Now, looking at the numbers on the left side, the smaller of the two numbers is the atomic number, and the larger of the two numbers is the mass number. Now, the atomic number is always equal to the number of protons. So because the atomic number is 13, we therefore have 13 protons. So we can eliminate answer choice C and D because they don't have 13 protons. To find the number of neutrons, the number of neutrons is equal to the mass number minus the atomic number. So in this case, it's going to be 27 minus 13. So therefore, we have 14 neutrons. So that really doesn't distinguish answer choice A from answer choice B. So now the last thing we need to look at is the number of electrons. Here's an equation that can help you to find it. The number of electrons is equal to the atomic number, I'm going to write AN for that, minus the charge. So in this case, the atomic number is 13 minus the charge of +3. So 13 minus 3 is equal to 10, and so therefore there are 10 electrons. Now it makes sense. If we were to add up the charges, we have 13 protons and 10 electrons. Now the charge of a proton is positive and the charge of an electron is negative. So positive 13 plus negative 10, that gives you a net charge of +3. So an ion with a positive charge has more protons than electrons. In this case, aluminum has 3 more protons than an electron in its ionic form. Number 2, what is the correct name for the compound N2O5? Now for each of these problems, feel free to pause the video and try these examples yourself and then unpause it to see if you have the right answer. Now, before I give you the answer for this compound, we need to talk about the naming rules for 2 different types of compounds. And that is for molecular compounds and for ionic compounds. N2O5 is a molecular compound. It's composed of nonmetals. Whenever you have a compound with a nonmetal with another nonmetal, it's a molecular or covalent compound. Electrons are being shared. Now let's say if we have aluminum chloride, AlCl3. This would be an ionic compound because it's between a metal and a nonmetal. Now for N2O5, we would use prefixes like mono, di, tri, tetra. Mono's for 1, di's for 2, tri's for 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, deca is 10. So for N2O5, it's dinitrogen, di for 2, pentoxide, penta for 5. So the correct answer is D for this particular problem. Now for aluminum chloride, AlCl3, we won't say aluminum trichloride. That won't be correct for AlCl3. You would simply name it aluminum chloride. So what you need to know for these type of problems is that whenever you're dealing with naming, if you need to name an ionic compound, you should not use prefixes like mono, di, tri, tetra. Rather, you just name it aluminum chloride. If it's a molecular compound where you have a nonmetal combined with another nonmetal, then you should use the prefix like mono, di, tri, tetra. So let's go over a few problems relating to this. So how would you name the compound SF6? So the first thing you need to do is you need to classify it. Is it ionic or is it molecular? So sulfur, is it a metal or a nonmetal? Sulfur is on the right side of the periodic table. The upper right side are composed of nonmetals, so sulfur is a nonmetal. Fluorine is also in the upper right corner of the periodic table, so it's a nonmetal too. Two nonmetals means that you have a molecular compound. So in this case, we do use prefixes such as mono, di, tri, tetra. Now to name it, we won't say monosulfur. For the first element, you don't use the word mono. So you could just simply say sulfur. And then for the second element, you do need to use a prefix. So for 6 represents hexa, so it's going to be sulfur, hexa, fluoride. So now let's say if you want to name this compound, MgF2. So magnesium is in the left side of the periodic table, so it's a metal. And fluorine is on the right side, so that's a nonmetal. A metal and a nonmetal is an ionic compound. So we won't use the prefixes mono, di, or tri, or tetra. So we won't say this compound is magnesium difluoride. That won't be correct. Rather, the correct name is, it's called magnesium. The first element, you just write its name, and the second element, you would add the end in IDE. So magnesium fluoride. Make sure you know your polyatomic ions, by the way, because if it's polyatomic, it could have the end in ite or ate. So make sure you review that. Number 3, calculate the percent composition of aluminum in aluminum sulfite. So the equation that you need for this problem is this. The percentage or percent composition of some element E is the mass of element E divided by the total mass times 100%. Because it's a ratio, if you use mass or molar mass, it doesn't matter, you're going to get the same answer. So we're going to use molar mass in this case. So the mass of aluminum, we want to find the percent composition for aluminum. So the mass of aluminum has to go on top. We have 2 aluminum atoms. So right now I'm just going to write 2Al divided by the total mass. So that's the sum of all the elements. So that includes the 2 aluminum atoms. We have 3 sulfur atoms, S times 3. And we also have 9 oxygen atoms. So notice that there's 3 oxygens here times the 3 on the outside. And then we're going to multiply it by 100%. So let's plug in the numbers. Aluminum, it's like 26.98 in the periodic table, but we're just going to make it a whole number. We're going to say it's 27. And then sulfur, we can round it to 32. And for oxygen, it's about 16. So times 100%. Now you can type this in all at once in your calculator, but for those of you who like to do it step by step, I'll take it one step at a time. So 2 times 27, that's about 54. If we add up all the numbers on the bottom, 9 times 16 plus 3 times 32 plus 2 times 27. You should get a total of 294. So 54 divided by 294 is about 0.18367, and then multiply that by 100%. You should get a percentage of 18.37%. So the closest answer is answer choice A. Now granted, if we were to use exact numbers like 32.06 or '07 for sulfur and 26.98, this would probably actually be 18.3, because right now our answer rounds to 18.4. But on a multiple choice test, as long as you get very close to the right answer, you should be fine. But that's how you calculate the percent composition of any element. Just take the mass of that element divided by the total mass of all the atoms in the compound, and then multiply that by 100%, and you should get the answer. Number 4, nitrogen gas reacts with hydrogen gas to form ammonia. Calculate the mass of ammonia, which is NH3, produced if 15 grams of nitrogen gas reacts with excess hydrogen gas. So the first thing we need to do is that we need to write a balanced chemical equation. Nitrogen gas is diatomic, so you can't write it as N. It's N2. And hydrogen gas is also diatomic. So make sure you know your diatomic elements. N2, H2, O2, F2, Cl2, Br2, I2. All of those elements are diatomic. And then it produces ammonia, which is NH3. Go ahead and take a minute to balance this chemical equation. To balance it, we need to put a 2 in front of NH3. So the nitrogen atoms are balanced. We have 2 nitrogen atoms on both sides. Notice that we have 6 hydrogens on the right side. 2 times 3 is 6. So we need to put a 3 in front of H2. So now it's balanced. Now this is a limiting reaction problem. We have the grams of nitrogen gas, and we really don't need the grams of hydrogen because it's excess. It's the excess reagent. The limiting reactant is the one that runs out first. So this is a gram to gram conversion. We need to convert from the grams of N2 to the grams of NH3. We want to find the mass of ammonia. And the best way to do this is to use stoichiometry. So let's start with what we're given, 15 grams of nitrogen gas. So now let's convert grams to moles. Whenever you want to convert grams to moles, you need to use the molar mass found in the periodic table. Nitrogen has an atomic mass of 14, so 2 nitrogen atoms would be about 28. So what this means is that 1 mole of nitrogen gas has a mass of 28.02 grams of N2. Nitrogen is about 14.01 if you want to be more precise. Notice that the units grams of N2 cancel. So right now we have moles. Our next step is to use the molar ratio. We need to convert from moles of N2 into moles of NH3. And to do that, whenever you want to change a substance, you need to use the coefficients in a balanced equation. So what these numbers tell you is that if 1 mole of N2 reacts, 2 moles of NH3 are produced. So because we have moles of N2 on top, we need to put that on the bottom. So for every 1 mole of nitrogen gas that reacts, 2 moles of ammonia are produced in this reaction. It's a 1-to-2 ratio. So now the units moles of N2, they cancel. And then our last step is to convert moles of NH3 into grams of NH3. So we need to use the periodic table once more. So hydrogen's about 1.01 on the periodic table. So 1.01 times 3 plus 14.01. NH3 has a mass of 17.04 grams per 1 mole. So the molar mass is always grams per 1 mole. So the units moles of NH3, they cancel. So now we can answer the question. So we need to type this in our calculator. 15 divided by 28.02 multiplied by 2 and multiplied by 17.04. So you should get an answer of 18.24 grams of NH3. And so that's how you can do a gram to gram conversion. Those 4 steps will be the same. You take the grams of, let's say, reactant A, convert it to moles, and then once you have moles, convert moles of reactant A to like moles of reactant or moles of product B. And once you have moles, you convert that to grams. So these 4 steps will be the same anytime you need to do a gram to gram conversion. So A is the correct answer for this particular problem. Number 5, 15 grams of sodium hydroxide is dissolved in enough water to produce a 250 milliliter solution. Calculate the molarity of the solution. Now, we're going to solve this problem 2 ways, using dimensional analysis or conversions, and using an equation, for those of you who prefer to use formulas and equations. So let's start with dimensional analysis. Now, what we need to know is that molarity is defined as the moles of solute divided by the liters of solution. So when you're using dimensional analysis, you need moles on top, liters on the bottom. So let's start with 15 grams of sodium hydroxide. Actually, first, we need to write the formula of sodium hydroxide. Sodium is in group 1 of the periodic table, so as an ion, it has a +1 charge. Hydroxide is OH with a -1 charge. Because these two, they have the same charge, the magnitude of the charges are the same even though the sign is opposite. Whenever you have 2 ions with the same charge, you can simply pair them together. So the formula of sodium hydroxide is simply NaOH. Now keep in mind, let's say if it was like magnesium hydroxide. Magnesium would have a +2 charge because it's in group 2 of the periodic table, and hydroxide has a -1 charge. So if the magnitude of the charges are different, you need to use this crisscross method, and then the formula would be MgOH2. Because if you mess up in the formula, the whole problem is gone. That's it, you won't get it right. So make sure you write the correct formula before you proceed. So let's begin. We have 15 grams of NaOH. And the first thing we're going to do is convert it to moles. So we need to find the molar mass of sodium hydroxide. So we need to add up Na plus O plus H. In the periodic table, Na has an atomic mass of about 23. And for oxygen, it's about 16. And hydrogen is about 1. So if we add 23 plus 16 plus 1, the molar mass of NaOH is about 40, or 40 grams per mole. So because grams is on the top left, we need to put it on the bottom right. So we're going to put 40 grams of NaOH on the bottom, and 1 mole of NaOH on top. So notice that the units grams of NaOH cancel. So now we have moles. Now, since we want to find molarity, we want to keep moles on top. We don't want to cancel it. So the last thing we need to do is divide by the liters. Now, we have the volume in milliliters. If you want to convert milliliters to liters, a quick way to do it is to divide by 1,000. So 250 milliliters, if you divide it by 1,000, is equal to 0.25 liters. You can divide it by 1,000, or you can move the decimal 3 units actually to the left. So if you move it 3 units to the left, you get 0.25 liters. So we're just going to divide it by 0.25 liters, and then this is going to give us our answer. So notice that we have moles on top, liters on the bottom, thus we have the molarity. So 15 divided by 40, and then take that result divided by 0.25, and your answer should be 1.5. So we have a 1.5 molar solution. Now, I'm going to calculate the same answer using formulas and equations. So the first equation that you need to know is that mass is equal to the moles times the molar mass. So whenever you need to find mass, molar mass, or moles, you can use this equation. So we know what the mass is. The mass of sodium hydroxide is 15. We need to find the moles. Here's why. The second equation that we're going to use is this one. Molarity is equal to the moles divided by the volume in liters. So in the first equation, we need to solve for moles. Once we get moles, we can plug it into the second equation. So 15 grams is equal to the number of moles, which in chemistry, moles is represented by the letter N. Think of PV equal nRT. So I'm just going to use N for moles, times the molar mass, which we already know that to be 40. So to solve for N, you got to divide both sides by 40. So N is 15 divided by 40. So the number of moles is equal to 0.375. So now that you have moles, we could divide it by the volume in liters. So the molarity is 0.375 moles divided by the liters, which is 0.25 liters. We've already converted the 250 milliliters into 0.25 liters. So you would have to do that here as well. And then you get the same answer, 1.5 m. So if you prefer to use equations, make sure you add these two equations to your formula sheet. For Gen Chem, as we go through an equation for every problem that we solve, make sure you write that down in your notes. So if you're taking like a final exam, or if you're studying for like the AP chemistry exam, make sure you write these equations down so they'll help you to like quickly review for your Gen Chem final. Number 6. How many milliliters of water must be added to 200 milliliters of a 0.75 molar solution of sodium hydroxide to dilute the concentration to 0.25 m? So this is a dilution problem. And anytime you see a problem where it's like molarity, volume, you can use the equation M1V1 is equal to M2V2. So the original solution has a molarity of 0.75. So that's going to be M1. And the volume of that solution is 200 milliliters. Now, the new solution, the diluted one, we want it to have a concentration of 0.25. So V2 is going to be the volume of that solution. So let's solve for V2. To do that, we need to divide both sides by 0.25. So these units, those values, they cancel. Now, 0.25 goes into 0.75 3 times. So if you divide 0.75 by 0.25, you should get 3. And then 3 times 200 is 600. So the entire left side is equal to 600. So that's V2. But now you have to be careful because the question asks how much milliliters of water should be added. If they were asking for the final volume, 600 would be the answer. But if they're asking how much water should be added, you need to take the difference between 600 and 200. So you got to add 400. So now let's make sense of this problem. So we know answer choice C is the correct answer. But here's the original solution. And then this is going to be like the diluted solution. So this is the old, and this is the new one. So originally the volume was about 200. And the concentration was 0.75. Anytime you add water to a solution, the concentration is going to decrease. Whenever you increase the volume by adding water, the molarity is going to go down. So we know the final volume is going to be 600. That's what we got from the equation. if we triple the volume, if you increase the volume by a factor of 3, the concentration should drop by a factor of 3. So notice that 200 times 3 is 600, but 0.75 divided by 3 is 0.25. So if you triple the volume, the concentration should decrease by a factor of 3. So now the question wanted to know how much water should we add to the original solution so that we can make this new solution with a concentration of 0.25. We realized that we need 600 milliliters of water. We have 200 already in the solution, so to go from 200 to 600, we simply need to add 400 milliliters of water. And so that's why that's the answer. So be careful with the wording of the question. If they wanted the final volume of the solution, it's 600. If they want to know how much water should be added, it's 600 minus 200, which is 400. Number 7. What is the correct oxidation state of chromium in sodium dichromate? So for this particular problem, we need to write an equation. So we have 2 sodium atoms plus 2 chromium atoms plus 7 oxygen atoms. I'm going to put the O in parentheses so it's not, you don't confuse it with 70. And this should all equal to a net charge of 0. If there was a net charge, we would place it here. But since there's no net charge in this compound, we're going to make it equal to 0. Now sodium is found in group 1 of the periodic table, so sodium usually has a +1 charge. For chromium, we need to solve it, so let's call it X. And oxygen usually has a -2 charge. So 2 times 1 is 2, and 7 times -2 is -14. So we can add like terms. 2 plus -14, that is -12. And then if we add 12 to both sides, those numbers cancel, so we get 2x is equal to 12. And then we need to divide both sides by 2. And so x is equal to 12 divided by 2 is +6. So that's the oxidation state of chromium. It's +6. So let's go over some examples relating to this. So let's say if you want to find the oxidation state of sulfur in sulfur dioxide. You'd write an equation, S plus 2 oxygen atoms equals to a net charge of 0. And oxygen, which is in group 6, usually has a charge of -2. So this is S minus 4 equals 0. If you add 4 to both sides, sulfur has an oxidation state of +4. Now what about phosphor in the phosphate ion, PO4 3-? What is the oxidation state? Now because we have a net charge, instead of setting the whole thing equal to 0, we're going to set it equal to -3, the net charge. And typically when oxygen is bonded to an element other than fluorine, it usually has an oxidation state of -2, unless it's in its pure elemental form, which in this case will be 0. Any element in its pure elemental form always has an oxidation state of 0. So 4 times -2 is -8, and if you add 8 to both sides, -3 plus 8, that's going to give you 5. So the oxidation state of phosphorus is 5. So here's some general rules. If you have a pure element like H2, N2, O2, the oxidation state is going to be 0. Now, fluorine in a compound is always -1. Oxygen is usually -2, except when bonded to fluorine, or if it's in the form of peroxide or superoxide. If you hear the word peroxide, oxygen has an oxidation state of -1, but 99% of the time it's going to be -2. So if it's oxide, it's -2, but if you hear the word peroxide, it's -1. Now hydrogen has an oxidation state of +1 when bonded to a nonmetal, but when hydrogen is bonded to a metal, it has an oxidation state of -1. So here are some examples. Calculate the oxidation state for sulfur in this compound, H2SO4. So we have 2 hydrogen atoms, a sulfur, and Actually, let's change it. Let's make it a little bit more interesting. Let's say find the oxidation state of sulfur in HSO4 minus. Try that one. So we have one hydrogen atom, a sulfur atom, and four oxygen atoms, and the net charge is -1. Now hydrogen, which is bonded to a nonmetal, has an oxidation state of 1. We're solving for sulfur, so we're going to call it X, and oxygen is usually -2. So we have 1 plus X minus 8, which is equal to -1. 1 minus 8 is -7. So if we add 7 to both sides, -1 plus 7, X is plus 6. So that's the oxidation state of sulfur. Go ahead and calculate the oxidation state of hydrogen in calcium hydride. So if we were to write an equation, we would have to set the net charge to 0. Now calcium is in group 2 of the periodic table, so it has a +2 charge. And so we're solving for hydrogen in this case. So since hydrogen is bonded to a metal, it's not going to be +1. If we move this 2 to the other side, if we subtract both sides by 2, we're going to get -2 on the other side. And if we divide both sides by 2, you can see that hydrogen has an oxidation state of -1 when it's bonded to a metal. When it's bonded to a nonmetal, like an acid, it's +1. And the last unusual case is hydrogen peroxide. This is the one case where oxygen is not 0 or -2. If you write an equation 2H plus 2O, and if you set it equal to 0, you need to plug in +1 for hydrogen because it's bonded to a nonmetal. So if we subtract 2 from both sides, we get 2 oxygen atoms, has a net charge of -2. And if we divide both sides by 2, you can see that oxygen has an oxidation state of -1 if it's in the form peroxide. But in the form oxide, it's -2. The only time oxygen has a positive oxidation state is when it's bonded to fluorine. If you solve for oxygen in this case, we're going to call it X. Fluorine always has a charge of -1 if it's not in its elemental form. So we have X minus 2 is equal to 0, and if we add 2 to both sides, this is the one case where oxygen has a positive oxidation state. So it has a +2 oxidation state in this particular example. So that's just a quick review of how to find the oxidation state of elements in compounds. Number 8. 38.6 milliliters of a 0.249 molar solution of sodium hydroxide was required to completely titrate 44.7 milliliters of a sulfuric acid solution. Determine the unknown concentration of the sulfuric acid solution. So notice that we have a molarity, a volume, and we're looking for another molarity given a different volume. So you can use M1V1 equals M2V2 for this particular equation. However, it's different from the last example that we did. In the last example, it was a dilution problem which contained only one substance, and that was sodium hydroxide. Or it might have been something else. But whatever the substance was, it only contained one substance. Now, for this particular example, we have two different substances. We have NaOH and sulfuric acid, H2SO4. So it's a little different, but you can still use the equation. So on the left side of the equation, we're going to use sodium hydroxide, and for the right side, it's going to be, we're going to apply the information that relates to H2SO4. So M1V1 is equal to M2V2. However, you have to take into account the molar ratio that's found in the balanced reaction of NaOH and H2SO4. But it turns out that we don't actually have to write the reaction to get the right answer. And notice that sodium hydroxide only has one hydroxide ion in it. So therefore, put a 1 in front of M1V1. And notice that H2SO4 has 2 protons, 2 hydrogens in it. So put a 2 in front of M2V2. If you do that, you're going to incorporate the molar ratio of this reaction, and you're going to get the right answer. Now, we're going to solve this problem two ways, using the equation and using dimensional analysis. So let's start with the equation first. So molarity 1, for this to work, we have to use the molarity for NaOH, which is 0.249. and the volume is 38.6 milliliters. The volume could be in milliliters or liters, but they simply have to match. If V1 is in milliliters, V2 has to be in milliliters. If V1 is in liters, V2 has to be in liters. Now we're looking for the second molarity. That's the unknown concentration of sulfuric acid. V2 is 44.7 milliliters. So now, to solve for M2, you need to multiply by 0.249 times, if you multiply 0.249 times 38.6, you should get 9.6114, and then divide it by 2 times 44.7. 2 times 44.7, that's like 89.4. And if you take 9.6114 divided by 89.4, you should get the answer. So the molarity of H2SO4 is 0.1075, or if you round it, 0.108. Now let's see if we can get the same exact answer. Using dimensional analysis. So we're looking for the concentration of H2SO4. So you don't want to start with the volume of H2SO4. Rather, start with the molarity of the other substance, sodium hydroxide. If you start with sulfuric acid, you're just going to make your life harder. So if you're solving for the concentration of sulfuric acid, start with either the volume or the molarity of the other substance. Now, to use dimensional analysis, we have to write a balanced reaction. So sodium hydroxide reacts with H2SO4, and it's going to produce, this is an acid-base neutralization reaction. And if you make a list of the ions that you have, Na has a +1 charge, hydroxide has a -1 charge. So in sulfuric acid, we have the H+ ion, and we also have sulfate, which has a -2. Whenever you pair up H+ and OH-, you're going to get H2O. And if we pair up Na+ with SO2, SO4 2-, I'm going to write it over here. So here's Na+, and here's SO4 2-. So we got to use that crisscross thing. So it's going to be Na2 SO4 1, but you don't have to write the 1. So now we have our equation. So now we just got to balance it. So notice that we have 2 sodium atoms on the right side, so we need a 2 in front of NaOH. And if you have 2 hydroxide ions, 2 hydrogen ions, you need 2 water molecules. Now it's balanced. So now let's start with the molarity of sodium hydroxide. When you're dealing with dimensional analysis, you don't want to write 0.249 capital M NaOH. Rather, you want to break down molarity into its 2 units. Molarity is moles over liters. So we're going to write it as 0.249 moles of NaOH per 1 liter. Because that's what molarity is. It's the moles per 1 liter of solution. Now we're going to multiply by the volume that corresponds to NaOH. And that's 38.6 milliliters. But because we have liters here, we need to convert it into liters. So to convert 38.6 milliliters into liters, you can divide it by 1,000 or move the decimal 3 units to the left, in which case it's going to be 0.0386 liters. So the units liters cancel. So we have moles of NaOH. Now we want to change from NaOH to H2SO4. Whenever you want to change from one substance to another, you need to use the molar ratio of the balanced reaction, which is a 2-to-1 ratio. So what this means is that for every 2 moles of NaOH that reacts, 1 mole of H2SO4 reacts with it. So because we have NaOH on the top, in the top left, we need it in the bottom right, so that these 2 units will cancel. Now we're looking for molarity. Whenever you're looking for molarity, and if you wish to do dimensional analysis to find it, you need to have moles on top and liters on the bottom. We want to find the molarity of H2SO4, so we already have moles on top, which means we don't want to cancel it on the bottom. Rather, we want to put liters on the bottom. Now, 44.7 milliliters, if we convert that to liters, if you divide it by 1,000, you should get 0.0447 liters. And we'll put a 1 on top. So we have moles on top, liters on the bottom. That's going to give us molarity. So now let's type in what we have. So 0.249 times 0.0386 divided by 2, enter, get that result, and then divide it again by 0.0447. And then you should get answer choice A, which is 0.1075. So now you know how to solve this problem both ways, using the equation if you think that's easier, or if you prefer dimensional analysis. Number 9. A 250 milliliter sample of argon gas has a pressure of 1.25 atm at a temperature of 300 Kelvin. Calculate the new pressure if the temperature is increased to 500 Kelvin and if the volume is decreased to 100 milliliters. So, look at the units that you have, and that can help you to determine what equation you need. So we have a volume, a pressure, and a temperature. And we're looking for a second pressure, we have a second temperature, and a second volume. So what equation has a P, a V, and a T in it? And another P, another V, and another T in it? It's probably this one. P1 V1 over T1 is equal to P2 V2 over T2, the combined gas law. So let's plug in what we have. P1, that's the first pressure, that's going to be 1.25 atm. The first volume is 250 milliliters, and the first temperature is 300 Kelvin. In this equation, volume could be milliliters or liters, but the units have to match. If V1 is in milliliters, V2 has to be in milliliters. Pressure could be in atm, it could be in torr, it could be in millimeters of mercury, but it has to match as well. So if P1 is in torr, P2 has to be in torr as well. However, the temperature has to be in Kelvin. It cannot be in Celsius. If you put it in Celsius, you will get it wrong. So don't do that. P2, the second pressure, we're looking for that. The second volume, that's going to be 100 milliliters. And the second temperature is 500 Kelvin. So what we're going to do is cross multiply. So if we multiply the 1.25, the 250, and the 500, we should get a big number, 15625. That does not look like a 2. 156250. And then if you cross multiply for the other side, P2 times 100 times 300. 300 times 100, that's basically 30,000. You just do 3 times 1 and you add the 4 zeros. And then times P2. So now we have to divide both sides by 30,000. So the second pressure has a value of 5.21 atm. And that's the end. That's it. That's all you got to do for this particular problem. So D is the correct answer choice. Number 10. Calculate the density of oxygen gas at STP. STP stands for standard temperature and pressure. At STP, the temperature is 0 degrees Celsius or 273 Kelvin, and the pressure is 1 atm. But also, something else that you need to know at STP is that 1 mole of a gas, it could be any gas, occupies a volume of 22.4 liters. With that knowledge, we can get the answer. Oxygen is diatomic, it's O2, and it has a molar mass of 16 times 2, which is 32 grams per mole. Look at the units. Notice that the units for our answer is like grams per liter. So with these two numbers, we can get the answer. So start with 32 grams of oxygen gas per 1 mole. That's the molar mass. That's what we have here. And then convert moles into liters. So notice that using this mole to liter ratio, we can say that 1 mole of oxygen gas occupies a volume of 22.4 liters. So the units moles cancel, and we have our desired units, which is grams on top, liters on the bottom. So to find the density of a gas at STP, all you need to do is take the molar mass and divide it by 22.4. So 32 divided by 22.4 is about 1.43. And so that's the density of oxygen gas at STP. Now there's another equation that you could use. Density is equal to the pressure times the molar mass divided by RT. Let's say if it wasn't at STP. But let's solve this problem. At STP, the pressure is 1 atm. If it's different, then just plug in a different pressure. The molar mass is 32 grams per mole. That's for oxygen. And then R is the gas constant. So we're going to use 0.08206. That particular gas constant has the units liters times atm over moles times Kelvin. There's another gas constant which is like 8.3145, but that has a different units. It has joules, moles, and Kelvin. If your pressure is in atm, you want to use this one. Notice that the units atm cancels, and moles cancel as well. The last thing we need to plug in is the temperature. At STP, the temperature is 273 Kelvin. So the units Kelvin cross out as well. So the only unit that we have now that's left over is it's grams over liters. And so that's going to give us the density. So if you type this in the calculator, 1 times 32 divided by 0.08206, and then take that result divided by 273, you should get 1.43 grams per liter. By the way, be careful with the way you type this in. If you're not getting the answer, when you divide by both numbers in the bottom, put this in one big parentheses. Because sometimes if you, let's say if you were to write it like this in your calculator, 1 times 32 divided by 0.08206 times 273. Your calculator is going to divide by this number and then multiply by 273. So that's a common mistake that students make. So make sure you put this in parentheses, and you should get the right answer. Number 11. Calculate the partial pressure of ammonia if 24 grams of nitrogen gas reacts with excess hydrogen gas at 298 Kelvin inside a 2.5 liter container. So notice that we have 3 different substances: ammonia, nitrogen gas, and hydrogen gas. So we need to write an equation. Nitrogen gas is N2, hydrogen gas is H2, and ammonia is NH3. So to balance it, let's put a 2 in front of NH3 and a 3 in front of H2. Now, our goal is to find the partial pressure of NH3. We have the temperature and the volume. What we need is the moles of NH3, but we have the grams of a different substance, N2. So we need to convert grams of nitrogen gas into moles of NH3. So let's start with 24 grams of N2 over 1. So to convert from grams to moles, you need to use the molar mass found on a periodic table. The molar mass of nitrogen is about 14.01. So for 2 nitrogen atoms, it's going to be about 28.02 grams per 1 mole of nitrogen gas. Now, our next step is to use the molar ratio. The molar ratio between N2 and NH3 is a 1:2 ratio. So for every 1 mole of N2 that reacts, 2 moles of NH3 are produced. So notice that the units grams of N2 cancel, as well as the units moles of N2 cancel. So we have our desired units moles of NH3. So now we need to take the calculator. So 24 divided by 28.02 times 2. You should get 1.713 moles of NH3. So now that we have the moles of NH3, we can now find the partial pressure of NH3. So we have moles, temperature, volume. To find pressure, we need to use the ideal gas law, PV equals nRT. So the volume has to be in liters. It's 2.5. N is going to be 1.713. R is the gas constant, 0.08206. Whenever you use this gas constant, your volume has to be in liters. It can't be in milliliters. And your pressure has to be in ATM. It can't be in torr or millimeters mercury. And the temperature has to be in Kelvin. So to get the answer, here's what you need to type in your calculator. It's 1.713 times 0.08206 times 298. Take that result and then divide it by 2.5. So the answer that I have is 16.76 ATM, which rounds to about 16.8. So answer choice C is the correct answer. Number 12. 4.722 grams of an unknown gas is collected over water inside a 2.75 liter container at 298 Kelvin. The total pressure inside the container is 749 torr, and the vapor pressure of water is 23.76 torr. Determine the identity of the unknown gas. Anytime you're trying to find the identity of the unknown gas, what you need to do is calculate the molar mass, and then you want to find the molar mass of every answer choice. So for hydrogen, the molar mass is 2. For CO2, the molar mass is 12 plus 16 plus 16, that's 44. For N2, it's 28. And for xenon, I think it's like 130 something. I have to look at my periodic table, and I don't have that with me, but it's somewhere, it's very high. So if I get a number that's 100 something, it's probably going to be xenon. But the goal is that we need to find the molar mass, and we can identify the compound. Now, to find the molar mass, we need to take the grams, which we already have, which is 4.722, and then divide it by the moles. To find the moles, we can use PV equal nRT, but we have to be careful because there's a lot of vapor in this problem. We don't only have one gas. There's 2 vapors that we have. We have the unknown gas, which I'll call partial pressure of the gas, plus the partial pressure of water. Anytime you have a collected over water problem, you have to consider the partial pressure of water. And this is going to equal the total pressure. The total pressure, we know it to be 749 torr. We need to find the partial pressure of the gas, and the vapor pressure of water is 23.76. So let's subtract 749 by 23.76. So the partial pressure of the gas is 725.24 torr. In order to use the ideal gas law, PV equal nRT, we need to convert that to ATM. So divide it by 760 to convert it to ATM. So this is equal to 0.9542 ATM. So now we can use the formula PV is equal to nRT. So let's plug in the partial pressure of the unknown gas, which we know it to be 0.9542. The volume, we have a 2.75 liter container. Our goal is to find N. Once we find the moles, we can find the molar mass. R is going to be the same, 0.08206, and the temperature is 298 Kelvin. Now to get the answer, this is what you need to do to get the moles. Multiply 0.9542 by 2.75, and you should get 2.62. Then divide that by 0.08206, and then you should get 31.977, and then take that result divided by 298 Kelvin, and then you'll get the moles. So N is equal to 0.1073 moles. Now, to find the molar mass, which I'll write as capital M, that's not molarity, by the way, Molar mass is going to be the grams divided by the moles. It has the units grams per mole. So let's take the mass, which is, we have 4.722 grams of the unknown gas, and let's divide it by the moles, 0.1073. So 4.722 divided by 0.1073, we get a molar mass of 44.0, which means that the unknown gas is carbon dioxide because it has a molar mass of 44. And that's what you need to do anytime you need to identify the identity of an unknown gas. Find the molar mass, take the grams divided by the moles, and that's it. Number 13, which of the following statements is not correct? So this is like a true or false problem. So A, the average kinetic energy of a sample of gas is dependent on temperature. That is a true statement. Kinetic energy is equal to or proportional to 3 over 2 RT. That's for a sample of gas. So as the temperature goes up, the average kinetic energy of a sample of gas will also go up. They're proportional. Now looking at D, the average velocity of gas particles is dependent on temperature. Is that true or false? It turns out that's another true statement. The root mean square velocity of a gas is equal to the square root of 3 RT divided by the molar mass, where the molar mass is in units not in grams per mole, but in kilograms per mole. And R for both of these equations is not 0.08206, but it's 8.3145 joules per mole per Kelvin. So as you can see, as temperature goes up, the root mean velocity will go up, which means that the particles will be moving faster at a higher temperature. So A and D are true statements, so we're down between B and C. Now looking at C, heavier gas particles exert a greater pressure on the walls inside of the container. Do you think that's true or false? It turns out that statement is false. We're going to consider two reasons for that. Let's kind of jump into physics. Now, you might be thinking, well, pressure is force divided by area. So the larger the force, the greater the pressure, right? And that is true. But you have to realize that heavier gas particles, they move slower. And even if you increase your mass but decrease your speed, it turns out that the pressure will be the same. If you go into physics and if you look at the impulse momentum theorem, the force multiplied by the contact time equals mass times the change in velocity. So assuming that the contact time is the same for like a heavy gas particle and a light gas particle, if we increase the mass and decrease the velocity, there's going to be no effect. The impulse, the force multiplied by the contact time is going to be the same. So you won't have a greater force if the contact time is the same. So therefore, heavier gas particles do not exert a greater pressure. Now another way you can see this is to use the equation PV equal nRT. Let's consider two samples of gases. Let's say we have hydrogen gas, which is a very light gas, and let's use a heavy gas like chlorine. Now let's say that they're at the same temperature, let's say 300 Kelvin, and we have the same quantity of gas, 1 mole. So 1 mole of chlorine gas, 1 mole of H2 gas, and let's say the volume of the container is the same. Let's say we have a 2-liter container. Will the pressure be the same or different if we have a lighter gas versus a heavy gas? Now looking at this equation, PV equal nRT, we have the same volume, which is 2 liters, same number of moles, which is 1, R is going to be the same, it's a constant, and the same temperature. So if the volume, if the volume, temperature, and moles are the same, based on the ideal gas law, P has to be the same as well, regardless if one gas is light or the other gas is heavy. Because molar mass is not part of this equation, the pressure is going to be the same for the light gas and the heavy gas. So therefore, heavier gas particles do not exert a greater pressure. So C is the false statement. Therefore, we're looking for the statement that is not correct, so C is the answer. Now, B is the true statement. The pressure inside a container is dependent on the total number of moles of gas. As we can see, moles is part of the equation. If we increase the moles of the gas, keeping everything the same, the pressure is going to increase. So B is the true statement. So the answer for this one is C. C is the false statement. Number 14, which of the following conditions will allow a real gas to behave more like an ideal gas? Is it high temperature, low temperature, high pressure, low pressure? What would you say? Now, let's start with a liquid. If we have a liquid, what's going to happen if we decrease the temperature? If we put it in a low temperature environment, like a freezer, what's going to happen? Eventually, the liquid will become a solid. And so low temperatures do not favor the formation of gases. But what's going to happen if we heat the liquid? Let's say if you were to boil water. Water is going to vaporize into steam, and so it's going to turn into a gas. As you can see, high temperatures favor the formation of a gas, so therefore a real gas will behave like an ideal gas at high temperature. So we can eliminate answer choice C and D. Now in a liquid, the molecules are relatively close, but not that close. In a gas, the particles are very far apart from each other. And in a solid, the molecules are very close together. So let's say if we have a container with gas. Now, let's say if we increase the pressure by decreasing the volume of the container. What's going to happen? So if we compress the container or compress the gas, will the gas turn into a liquid, or will it become more gas-like? What would you say? As you can see, because the gas particles are more compressed, they look more like a liquid. So high pressure doesn't favor the formation of a gas. If you increase the pressure, it's going to go this way. High pressure favors the formation of a liquid. If you compress the gas, it eventually converts to a liquid. Low pressure favors the formation of a gas. So a real gas will behave more like an ideal gas at high temperatures and low pressures. The answer is A. So let's review. Let's say if you have a solid. If you add heat to it, it's going to go from a solid to a liquid, and if you add more heat, it's going to go to a gas. So therefore, high temperatures favor the formation of gases. So real gas behaves as an ideal gas at high temperatures. Now, if we were to increase the pressure, increasing the pressure will compress a gas into a liquid. And if you add more pressure, it can go down to a solid. So high pressure favors the formation of solids, but low pressure favors the formation of gases. If you decrease the pressure, the solid will eventually become a gas. Another way you can see this is by looking at the phase diagram, which usually looks something like this. So this is the solid, this is the liquid, this is the gas. And on the y-axis we have pressure, on the x-axis we have temperature. So let's say if we start from here. If we increase the temperature, we're going to go from a solid to a liquid, and eventually from a liquid to a gas. So high temperatures favor the formation of gases. You can see the gases down the right side. Now, let's say if we started from this point here. Let's extend this line further. Let's say if we're to increase the pressure, that means we have to go up the y-axis. So if we increase the pressure, the gas will eventually become a liquid, and then the liquid will eventually become a solid. So high pressures favor the formation of solids. High temperatures favor the formation of gases. So if you want to get a good gas, or if you want a gas to behave like an ideal gas, you need a high temperature and a low pressure. Number 15. How much energy is required to heat 75 grams of water from 25 degrees Celsius to 74 degrees Celsius? And a specific heat capacity of water is 4.184 joules per gram per Celsius. So you need to know the right equation to use, and it's Q equals MCAT, or MC delta T. Q represents the heat energy, M is the mass in grams, C is the specific heat capacity, and delta T is the change in temperature, final temperature minus the initial temperature. So let's plug in the numbers that we have. So the mass is 75 grams, the heat capacity is 4.184, and the temperature difference, final minus initial, 74 minus 25. So 74 minus 25, that's 49, and then we're going to multiply that by 4.184 and 75. And you should get 15,376. Now, what are the units for this number? Is it in joules or kilojoules? Now, Q is in joules because the specific heat capacity is in joules. If you look at the units, the mass is in grams, the specific heat capacity is joules per gram per Celsius, and the temperature is in Celsius. The temperature can also be in Kelvin, by the way, for this particular equation. The units Celsius will cancel and grams will cancel, and so Q is in joules. But notice that the answer is in kilojoules. So to convert joules into kilojoules, divide by 1,000. So you should get 15.4 kilojoules. So answer choice D is the correct answer. Number 16. How much heat energy is required to melt 25 grams of ice? The heat of fusion for ice is 6.01 kilojoules per mole. Now, the equation for this type of problem, whenever you have a phase change, there's two types. It can be moles times the enthalpy of fusion, if it's in kilojoules per mole, or it could be mass times the enthalpy of fusion, if the units are like joules per gram or something. So it really depends on the unit. What we can do in this problem is we can simply convert grams to moles and moles to kilojoules. And I think that's the best way to solve it. So let's start with 25 grams of ice. And let's convert it into moles. Now water has a molar mass of approximately 18. Hydrogen is 1, there's 2 of them, so that's 2, and oxygen is 16, so that's a molar mass of 18. So we have 18 grams of water per 1 mole. So the units grams cancel. And next, we're going to convert moles into kilojoules using this number. So this number means that for every mole of ice that you melt, it requires 6.01 kilojoules. So the units moles cancel. And so now we can find the answer. So it's going to be 25 divided by 18 times 6.01. And you should get 8.347 kilojoules. Now, is the answer positive or negative? So as you go from a solid to a liquid, as you melt ice into liquid water, is that an endothermic process or an exothermic process? Well, you have to add heat to melt ice. So because the ice cube has to absorb heat, it's an endothermic process. And for an endothermic process, the enthalpy is positive, so this is going to be a positive answer. The ice cube needs to absorb 8.347 kilojoules of heat to melt into liquid water. And the reverse is true. If you want to freeze liquid water into ice, you have to remove heat, so that would be an exothermic process. So freezing is exothermic, and melting is an endothermic process. So for this problem, the correct answer is answer choice B. Number 17. Which of the following represents the phase change from a gas to a solid? Now this is something you have to know. The answer for this is deposition. So let's review all the different phase changes. So from a solid to a liquid, it is called melting. Think of an ice cube turning into liquid water. It melted. Now, from a liquid to a gas, this is known as vaporization. And from a solid directly to a gas, this is called sublimation. Melting, vaporization, and sublimation, as you go from a solid to a liquid to a gas, these processes are endothermic. The enthalpy will be positive. So now, let's say if you wanted to go from a liquid to a solid. What happens when you put a cup of water in the freezer? It freezes. So liquid to a solid is known as freezing. And a gas to a liquid is known as condensation. And gas to solid is called deposition. So as you go from a gas to a liquid to a solid, all three of these processes are exothermic. So the enthalpy is negative. So energy is released for an exothermic process. Number 18, calculate the enthalpy of the combustion of ethanol using the following information. So to find the enthalpy of the reaction, we need to use this equation. Delta H is products minus reactants. So on the product sides, we have 2 carbon dioxide molecules and 3 H2O molecules, minus the reactants, which are C2H5OH plus 3O2. So now we can plug in what we have. So we have 2 carbon dioxide molecules, each with a value of negative 393.5. Plus we have 3 water molecules, and each with a heat of formation of negative 285.9. Now the value for ethanol is negative 277. And oxygen is a pure element in its standard state, so it has a enthalpy of formation of 0. So now let's plug these numbers into the calculator. So 2 times negative 393.5, that is equal to negative 787, and then 3 times negative 285.9, that's about negative 857.7. And then here, don't forget to distribute the negative sign, so it's going to be plus 277. So if we add these 3 numbers, we should get a total of negative 1367.7. The closest answer that we have to it is answer choice A. So A is the correct answer for this problem. Number 19, calculate the amount of heat energy released if 10.5 grams of propane reacts with excess oxygen according to the following chemical equation. So this equation is already balanced. So we just need to find the energy in kilojoules, and we're given grams. So here we have a thermochemical equation, and in such a problem, you can convert grams to moles, moles to kilojoules. So let's start with the 10.5 grams of C3H8. Whenever you need to convert grams to moles, you need the molar mass. So 3 carbon atoms, carbon's about 12, so 3 times 12, that's 36, and plus 8 for the 8 hydrogen atoms. So propane has a molar mass approximately about 44. So 44 grams per 1 mole. So the grams of C3H8 will cancel. Now, in a thermochemical equation, you can convert moles into kilojoules by using this number with the balance equation. Now, since we want to convert moles of C3H8 into kilojoules, we need to use this coefficient. If we had oxygen, we would use 5. If we had CO2, we would use 3. So 2200 kilojoules will be released for every 1 mole of propane that burns in this reaction. So we get this number from the balanced chemical equation. So now we just got to plug it in. So it's going to be 10.5 divided by 44 times 2200. So the answer that I got is 525 kilojoules. And it's negative. So the answer is answer choice A. Now granted, if I were to use exact numbers, like carbon is really 12.01, the answer would be closer to 530. But if you use rounded values, you can still get the right answer if the choices are not too close from each other. So that's it. That's what you got to do for this problem. Number 20. Calculate the energy of a photon that has a wavelength of 451 nanometers. There are 2 equations that you need. The energy is equal to Planck's constant times the frequency. And the wavelength times the frequency is equal to the speed of light. So first, well actually we can combine these 2 equations. So if you solve for V, The frequency is the speed of light divided by the wavelength. So we're going to replace the V with that. So to find energy directly from wavelength, you can use this equation. It's E equals H times C divided by lambda. So now let's plug it in. So the energy is going to be Planck's constant 6.626 times 10 to the negative 34 times the speed of light, which is 3 times 10 to the 8 meters per second, all divided by the wavelength. Now the wavelength is in nanometers, so you got to convert it to meters. If it's in nanometers, this is all you need to do. Rewrite 451, but add times 10 to the negative 9. So now it's in meters. And then once you type this in, you're going to get the answer. So it's going to be, we're just going to plug it in the way it is, and you should get 4.408 times 10 to the negative 19 joules, if you typed it in correctly. So the correct answer for this problem is answer choice B. Number 21, what is the ground state electron configuration of fluorine? Now, if you have a multiple choice test, the quickest way to find the ground state or the right answer is to use the atomic number. The atomic number of fluorine is 9. So for the electron configuration, the exponents must add up to 9. Looking at answer choice A, it's 1s2, 2s2, 2p3. If we were to add the exponents, 2 plus 2 plus 3, we would get 7, so it's not A. Looking at B, if we add 2 plus 1 plus 5, that will give us 8, so it's not B. And for C, which is 1s2, 2s2, 2p5, if we add up 2 plus 2 plus 5, it gives us a total of 9. C is the correct answer. Fluorine has this electron configuration. Number 22. Which of the following 4 sets of quantum numbers correspond to the last electron found in nickel? Well, the first thing we need to do is find the electron configuration of nickel. So nickel, based on the periodic table, has an atomic number of 28. Now, we're going to write out the sublevels so we can write the electron configuration for nickel. So first you have 1s, then there's 2s, 2p, 3s, 3p, 3d. The third level has 3 sublevels, and the fourth level has 4s, 4p, 4d, 4f. And hopefully we don't need to go past that. So S can only hold 2 electrons, P can hold 6, D can hold 10, F can hold 14. Now, we need to write the electron configuration until it adds up to 28. So first we have 1s2. We're going to add the exponents. After 1s, we have the 2s sublevel, so 2s2. And then after 2s is going to be 2p, then 3s. P can hold up to 6, so it's going to be 2p6, 3s2. If we add the exponents right now, 2 plus 2 plus 6 plus 2, right now we have a value of 12. So after 3s, we have 3p and then 4s. So 3p6, p can hold up to 6, 4s2. After 4s, we have the 3d level. So right now we have a total of 20. 2 plus 2 plus 6 is 10, and 2 plus 6 plus 2 is 20. So we need 8 more, and the D sublevel can hold up to 10, so the last one that we need is 3d8. If you add all the electrons, it's 28 at this point. So that is the electron configuration for nickel. The very last electron in the nickel atom is the 3d8 electron. So we need to find what the 4 quantum numbers are for that 3d8 electron. So focusing on the 3, n is 3. Whatever that first number that we have, that's the n value. For the s sublevel, L is 0. For P, L will always be equal to 1. For the D sublevel, L is 2. And for F, L will be 3. So because it's 3D, we know L is 2. So we can eliminate C and we can eliminate B. So we're between A and D. Now looking at A and D, the ml value is both 0, but the ms value is different, negative a half versus positive a half. The answer for this problem is going to be A, but I'm going to show you why it has a spin of negative a half. So for the 3d8 electron, we said that n was equal to 3 because of this number, and for the d sublevel, L is equal to 2. Now when L has a value of 2, ml can be anywhere from negative 2 to 2. The d sublevel has 5 orbitals. The first one has a value of negative 2, the second one is negative 1, 0, 1, and 2. So we need to fill up 8 electrons since we have 8 in the d level. So we're going to start with the up arrows. So 1, 2, 3, 4, 5, 6, 7, 8. This is the 8th electron. Now notice that it's in the 0 orbital, so that means ml is equal to 0. And also notice that we have a down arrow. For a down arrow, the spin is minus a half, and that's why the answer was A. But let's go over some examples. So let's review a few things. So keep in mind, whenever you have the S sublevel, L is equal to 0. And S only has one orbital, so that means ml is also equal to 0. For the P sublevel, L is 1. And whenever L is 1, ml could be 3 values. P has 3 orbitals. And ml can be negative 1, 0, and 1. We talked about D already. It has 5 orbitals. So for the D sublevel, L is 2. And for the 5 levels, ml can be anything from negative 2 to 2. And the last one is the F sublevel, where L is 3. Whenever L is 3, ml can be anywhere from negative 3 to 3. The F sublevel has 7 orbitals. So let's say if you want to find the 4 quantum numbers for the, let's say the 4p2 electron. So n is the first number that you see, 4. For the p sublevel, L is going to be 1. And the p sublevel has 3 orbitals. If L is 1, ml could be negative 1, 0, or 1. So those are the ml values. And because we're focused on the second electron, we're going to draw just 2 arrows. So the second electron is in the orbital where ml is equal to 0. And because it's an up orbital, an up arrow, the spin is positive 1/2. So let's look at another example. Let's say if we have the 4f13 electron. Using the information that we just considered, go ahead and find the 4 quantum numbers that corresponds to this electron. So n is 4. For the F sublevel, L has to be 3. Now, for F, there are 7 orbitals actually, with a value ranging from negative 3 to 3. And a 13 electron lands in, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So here's the 13th electron. It's in the orbital that has a value for ml, which is 2. And because it's facing in a downward direction, the electron spin is minus 1/2. So that's just some background information on quantum numbers and how they work. Number 23. Which of the following 4 sets of quantum numbers are incorrect? Is it A, B, C, or D? Typically, the first thing I look at is the electron spin. The electron spin can only be either plus or minus 1/2. If you see any other numbers other than this fraction, you know it's wrong. So if you were to see ms equals 1, you could eliminate that answer. So looking at the spin, for all of them it's a fraction, plus or minus 1/2, so all of those numbers are acceptable. The second thing you can do is compare n and l. Now L has to be less than or equal to n minus 1. So what this means is that if n is 4, L cannot equal 4 or anything more than 4. If n is 3, L can equal 2 or anything less than 2. It could be 2, 1, or 0, but it can't equal 3 or 4. So looking at A, n is 3, L is 2. L has to be at least 1 less than n, so A is okay. Same is true for C. For B, if n is 4, L is 0. And D, if n is 4, L is 3. As long as n is greater than L, at least by a factor of 1, it's okay. Now the last thing we need to look at is the ML values, the orbitals, or the magnetic quantum number. ML has to be between negative L and L. So what this means is that, let's say if L has a value of 2, that means ML has to be between negative 2 or 2. So looking at D, if L is 3, ML could be anywhere from negative 3 to 3. That means it could be negative 3, negative 2, negative 1, 0, 1, 2, or 3. And ML is negative 1, so that's okay. So D is fine. Looking at, let's see, answer choice A, if L is 2, ML could be 0, because ML could be negative 2, negative 1, 0, 1, and 2. Same is true of C. The only thing that doesn't work is B. When L is 0, ML can be only one value, 0. It can't be negative 1. So B is the one that's incorrect. So just to review, whenever L is 0, ML can only be 0. This is the S sublevel and there's only one orbital. So ML cannot equal negative 1. Now, if L were to equal 1, this would be the P sublevel, which has 3 orbitals, and ML could be negative 1, 0, or 1. And so this would have worked if L was 1, but since L is 0, ML can't be negative 1. Number 24, how many orbitals are in the n equal 4 principal energy level? The equation that you need is this. The number of orbitals is equal to n squared. So that's 4 squared, which is 16. So D is the correct answer. Now you might be wondering, okay, why does that equation work? In the first energy level, where n is equal to 1, all we have is the 1s level. In the second energy level, when n is 2, we have the 2s sublevel and the 2p sublevel. When n is 3, we have the 3s level and the 3p sublevel and the 3d. For the fourth energy level, we have 4s, 4p, 4d, and also 4f. Now, the 4s energy level can hold, well, let's start with 1. The first energy level can hold up to 2 electrons. And for every 2 electrons, you only have 1 orbital. So the 1s level has only 1 orbital. Now we know that S has 1 orbital, but P has 3 orbitals, which is a total of 4 orbitals in the second energy level. Notice that the total electrons that we have is 8. And if you divide 8 by 2, you get 4, because there's only 2 electrons that can be in a single orbital. For the third energy level, if we add up the orbitals, S can hold 1, P can have 3 orbitals, D has 5. That gives us a total of 9. And for the fourth energy level, if you add up all the electrons, you should get 32. Half of that is 16. S has 1 orbital, P has 3 orbitals, D has 5, F has 7. If you add those numbers, you get 16. So notice that the number of orbitals is equal to n squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And that's how it works. But if you want to see it visually, the 4s level has only one orbital, the 4p level has 3, 4d has 5, and 4f has 7. So therefore we have a total of 16 orbitals in the 4th energy level. By the way, the video that you're currently watching is the first 2-hour trailer version of a longer 8-hour video. So this video currently has only 40 multiple choice problems, but the entire video has 160 multiple choice problems. So I'm going to post a link which you can access the entire video, and any topics that we missed in this trailer version, you can find it in the other video for the most part. So I'm going to post that link, and then you can check it out when you get a chance. Number 25. Which of the following choices correctly ranks the different forms of electromagnetic radiation in order of increase in wavelength? So you need to know it in this order. All the way to the left we have radio waves, after which we have microwaves, and then infrared radiation, and then visible light. So after infrared it's red light, orange or Roy G. Biv, yellow, green, blue, and then violet. After violet, next comes ultraviolet radiation, and then you have X-rays, and then finally after X-rays, gamma rays. To the left, radio waves have the longest wavelength. I'm going to put the lambda symbol for wavelength. And to the right, gamma rays have the most energy, and they also have the highest frequency. So these are some things that you want to know with regard to electromagnetic radiation. So based on a question, we want to rank it in order of increase in wavelength. So radio waves have the longest wavelength, and gamma rays have the shortest. So looking at that, we could see it's answer choice A. Gamma rays have the shortest wavelength. Next, X-rays. After X-rays is ultraviolet, and then after ultraviolet is visible light. So out of those 4, visible light or light waves, they have the longest wavelength. Gamma rays have the shortest wavelength. And that's it for this particular problem. Number 26. Which of the following elements has the highest first ionization energy? Is it helium, fluorine, oxygen, or chlorine? Ionization energy is the energy that is required to remove a valence electron from a gaseous atom. It could be just the outermost electron. Sometimes it could be a core electron, depending on if it's like the second or third ionization energy. But it's the energy required to remove the outermost electron, which is usually a valence electron. So ionization energy increases as you go this way in the periodic table. So it increases as you go up a column or to the right. Now oxygen, so on the periodic table we have carbon, nitrogen, and then oxygen, and then fluorine. And below fluorine we have chlorine, and then here's like neon, and then helium is over there. So notice that helium has the highest ionization energy compared to oxygen, fluorine, and chlorine. Helium is to the right of all the elements, and it's above it as well. So if we were to rank it, helium would have the highest, and then the next one would be fluorine, and then after that we have oxygen and chlorine. So the correct answer for this problem is answer choice A. By the way, just to review the other trends, atomic radii or atomic size increases as you go this way in the periodic table. So as you go to the left and down, it increases. Electronegativity increases towards fluorine. Fluorine is the most electronegative element. And metallic character increases as you go to the left and down. So those are some other periodic trends that you want to be familiar with. Number 27, which of the following molecules has a trigonoplanar molecular geometry? Is it A, B, C, or D? So let's draw each one. Let's start with sulfur dioxide. Sulfur has 6 valence electrons, and oxygen also has 6, but we have 2 of them, so there's a total of 18. Now, for molecules that do not contain hydrogen, there's a way that you can calculate the number of lone pairs or electrons on their center atom. If you take 18 and subtract it by the highest multiple of 8, just under 18, you'll get the number of electrons on the center atom. So multiples of 8 are 8, 16, 24, 32, but the highest of this that's under 18 is 16. So if we take 16 from 18, we get 2. What this tells us is that sulfur has 2 electrons, or 1 lone pair, on it. And it also has 2 oxygen atoms. Now, sulfur can have what is known as an expanded octet. It turns out that elements that usually have expanded octets, like third row elements like phosphorus, sulfur, and chlorine, the number of bonds and dots that are on that element is usually equal to the valence electrons. So because sulfur has 6 valence electrons, it's going to have a total of 6 bonds and dots. Since it already has 2 dots, it's going to have 4 bonds. So 1, 2, 3, 4. The exception to this is if sulfur has a formal charge. Now, whenever oxygen has 2 bonds, it requires 2 electrons, or 2 lone pairs. I meant 4 electrons, 2 lone pairs. So notice that every oxygen atom has 8 electrons. If you add up all the electrons, you should get a total of 18. And that's the Lewis structure for sulfur dioxide. And it has a bent molecular geometry. Now, CH4. For most carbon-hydrogen compounds, we really don't need to add the electrons, but if you wanted to, carbon has 4 valence electrons, hydrogen has 1 times 4. We should get a total of 8. Hydrogen can only form a single bond, so this is the only way we can draw it. And as you can see, each bond represents 2 electrons, so we have a total of 8 electrons. Methane has a tetrahedral molecular geometry. And keep in mind, for a tetrahedral structure, the bond angle is about 109.5. For SO2 is less than 120. Now, BF3. Boron has 3 valence electrons. Fluorine has 7 times 3, 24. 24 is a multiple of 8, so that tells us that there are no lone pairs on the central boron atom. That multiple of 8 rule works pretty well if there's no hydrogens involved, because hydrogen can only have 2 electrons and not 8. Now, fluorine wants to have 8 electrons. Each fluorine atom has 1 bond, so we need to add 3 lone pairs, so that every fluorine atom has 8 electrons. 8 times 3, we get 24. And that's the Lewis structure of BF3, and it is the correct answer. It has a trigonoplanar molecular geometry and a bond angle of 120. Now, for NH3, the multiple rule of 8 thing doesn't work whenever you have hydrogen. Nitrogen has 5 valence electrons, and hydrogen has 1 times 3, so we get a total of 8. Now, hydrogen can only form 1 bond. So right now that's 6 electrons. To get 8, we need to add a lone pair. So that's the Lewis structure for NH3, and it has a trigonal pyramidal structure with a bond angle of 107. So it's not trigonoplanar, but trigonopyramidal. So C is the correct answer for this problem. Number 28. Which of the following molecules has sp3 hybridization around the central atom? Is it water, BF3, BRF3, or sulfur hexafluoride? Let's start with SF6. Let's draw the Lewis structure. Sulfur has 6 valence electrons, and fluorine has 7 times 6, which is 48. Now, because 48 is a multiple of 8, there are no lone pairs on the central sulfur atom. So SF6 looks like this. And each fluorine atom has 3 lone pairs. So if you add up the total electrons, you should get 8 times 6, which is 48. The molecular geometry for this compound is octahedral. The bond angle is about 90 degrees all around. And the hybridization is S1P3D2. Notice that the exponents add up to 6. 1 plus 3 plus 2 is 6, because the sulfur has 6 groups attached to it. So sometimes it could be written as D2 SP3. You might see it written that way as well. Now let's look at BrF3. Bromine has 7 valence electrons, and fluorine also has 7 times 3, so we get a total of 28, which is not a multiple of 8. So we're going to subtract that number by the highest multiple of 8, just under 28. So multiples of 8 are 8, 16, 24. So if we subtract 24 from 28, we get 4. So what this tells us is that bromine has 4 electrons, or 2 lone pairs. And it has 3 fluorine atoms, each of which has 3 lone pairs as well. But I'm not going to draw the lone pairs. But just know that fluorine each have 3 lone pairs. So if you add up all the electrons, you should get a total of 28, including the 3 lone pairs on each fluorine atom. Now, the molecular geometry for this compound is, it has a T shape. And if you were to look at the hybridization, bromine has 5 groups. It has 3 fluorine atoms and 2 lone pairs. So for 5 groups, the hybridization is S1P3D1, which adds up to 5. So it's not C and it's not D. Now looking at B, we know that boron trifluoride looks like this because we drew it in the last example. And so boron has 3 groups, so therefore it has an S1P2 hybridization. 1 plus 2 is 3. So the answer must be water. If we draw water, water has 8 valence electrons. Hydrogen has 1, and there's 2 of them. And oxygen has 6 valence electrons, so for a total of 8. And right now we have 4 electrons. Each bond represents 2, so we need 2 more lone pairs. And that's the Lewis structure for water. It has a bent shape. And notice that water has 4 groups. It has, the oxygen atom has 2 hydrogens and 2 lone pairs. So for 4 groups, the hybridization at the central atom is S1P3. 1 plus 3 equals 4. So the correct answer is A. It has an sp3 hybridization around the central oxygen atom. Number 29. Which of the following molecules is polar? Is it A, B, C, or D? If we were to draw the Lewis structure for CH4, methane, this molecule is nonpolar due to the symmetry that it has. Typically, whenever you have a carbon-hydrogen bond, it's relatively nonpolar. The electronegativity value for carbon is like 2.5, and for hydrogen is 2.1. So if the electronegativity difference is less than 0.5, the bond is nonpolar. So A is eliminated. Now for carbon dioxide, if we were to draw the Lewis structure, it would look something like this. It has a linear molecular geometry. Now the carbon-oxygen bond is polar. Carbon has an electronegativity value of 2.5, and for oxygen it's 3.5. So the EN difference is much larger than 0.5, so it has a polar bond. Oxygen has a partial negative charge because it's more electronegative than carbon. So if you were to draw the dipole moment, the arrow would point towards the more electronegative oxygen atom. But notice that these arrows are opposite to each other, and therefore they cancel. And so the net dipole moment for this molecule is 0. Therefore, even though it has polar bonds, overall, CO2 is a nonpolar molecule. Now, for boron trifluoride, the situation is similar as well. fluorine is much more electronegative than boron, and so it has a partial negative charge. And so the bonds are very polar. However, due to the symmetry of this molecule, all of the arrows, they point in opposite directions, and so they all cancel out, and therefore this is a nonpolar molecule. If you're wondering why those arrows cancel out, let's go back to physics. You have an arrow going this way, and an arrow going this way, and another one going this way. Now looking at the arrow on the bottom right, it has two components. It has a y component and an x component. And the same is true for the arrow on the left. It has a y component and an x component. These two x components are opposite to each other, so they cancel. And these two y components cancel with the larger one on top. So all of it cancels and it's nonpolar. The only one that is polar is NF3. If you draw the Lewis structure, it has a lone pair, and the dipole moments do not cancel. Let's add up the valence electrons first for NF3. Nitrogen has 5 valence electrons. It's in group 5A of the periodic table. And for fluorine, it has 7. 7 times 3 is 21 plus 5. You get a total of 26. And if you subtract that by the highest multiple of 8, just under 26, 8, 16, 24, you get 2. So what that number tells you is that nitrogen has 2 electrons, or 1 lone pair. And every fluorine atom has 3 lone pairs because they want to have 8 electrons. And so the total number of electrons in a structure is 26. We have a trigonal or trigonal pyramidal structure. Now, fluorine is much more electronegative than nitrogen. It has a value of 4.0, and for nitrogen is 3.0. So fluorine bears the partial negative charge, nitrogen bears the partial positive charge. So if we were to draw the dipole moment, it would point towards the fluorine atom. So notice that we have 3 arrows going in the, for the most part, the general downward direction. And so these arrows do not completely cancel for the most part. They're going towards the bottom. And so there's a net dipole moment. And also the presence of this lone pair also contributes to the polarity of this molecule. So NF3 is a polar molecule. It has a net dipole moment. Number 30. Rank the following intermolecular forces in order of decrease in strength. What you need to know is that hydrogen bonds are stronger than dipole interactions, which are stronger than London dispersion forces. So the correct answer is answer choice B. Now you have hydrogen bonds whenever H is directly attached to nitrogen, oxygen, or fluorine. Dipole interactions occur whenever you have a polar molecule. So dipole-dipole interactions occur between 2 polar molecules. LDF, London dispersion forces, also known as van der Waals forces, they're found in everything, but they are the most important interaction in nonpolar molecules. So let's say if you were to have a compound like water. Water has hydrogen bonds, so it has an OH bond, so it has hydrogen bonds. Anything that has hydrogen bonds is polar, so it has dipole interactions, and it also has LDF, which is found in everything. Now let's say if you have a polar substance like SO2. SO2 would contain dipole interactions, plus it would also contain LDF. But if they ask you which one is the strongest intermolecular force in SO2, you would choose dipole interactions. For water, you would choose hydrogen bonds. Now let's say if you have like methane. Anytime you have a substance that contains only carbon and hydrogen bonds is nonpolar. The only intermolecular force that's found in methane would be like LDF, dispersion forces or van der Waals forces. Number 31. Which of the following molecules has the highest boiling point? Now, if we look at A, we have a compound that is completely nonpolar. It only contains carbon and hydrogen bonds. So when it's nonpolar, the only force that it has is London dispersion forces. Now, compound D is also nonpolar, and so it has London dispersion forces only. So therefore, these two which contain the weakest of the intermolecular forces, they're going to have the lowest boiling point. So we could eliminate answer choice A and D. Now, B, we have a sulfur. And if we were to draw the Lewis structure, there's a sulfur group, a hydrogen, and a methyl group, which is a CH3, and it has 2 lone pairs. So this molecule is polar. It has a bent shape similar to that of water. And because it's polar, it's going to have dipole interactions. So it's going to have a higher boiling point than A or D. Now looking at answer choice C, methanol, we have an OH bond. So methanol has hydrogen bonds. And hydrogen bonds are stronger than dipole interactions, so therefore we should expect that methanol should have the highest boiling point because it has the strongest of the intermolecular forces. So it has H bonds. So C is the right answer. Number 32. 25 grams of sodium hydroxide is dissolved in 300 grams of water. Calculate the molality of the solution. Now, molality is different from molarity. Molarity with an R is the number of moles of solute divided by the liters of solution. Molality is the moles of solute divided by the kilograms of solvent. So let's find the moles of solute and let's divide it by the kilograms of solvent. Water is a solvent. It dissolves the sodium hydroxide. And we have 300 grams of water. So how many kilograms is that? To convert grams into kilograms, you could divide by 1,000 or move the decimal 3 units to the right. So 300 grams is about 0.3 kilograms. Let's start with 25 grams of sodium hydroxide. And let's convert it to moles. To convert grams to moles, you need the molar mass. According to the periodic table, sodium has an atomic mass of 23, and for hydrogen it's about 1, and for oxygen is 16. So NaOH has a molar mass of 40 grams per 1 mole. So notice that the units grams of NaOH cancel. So right now we have moles. So now we got to divide it by the 0.3 kilograms of solvent. So whenever you have moles on top and kilograms of solvent on the bottom, that's going to give you the molality. So 25 divided by 40 is about 0.625. That's how many moles we have. And if we take that number of moles divided by 0.3 kilograms, we get a molality of 2.08. So D is the right answer. Number 33. Calculate the molality of a 24% HCl aqueous solution. So how would you do that? When you have a mass percent, a 24% HCl solution, what you need to realize is that you have 24 grams of HCl per 100 grams of solution. Now the solution has 2 components, the solute and the solvent. The solute plus the solvent is equal to the solution. Now because we have an aqueous solution, the solvent is H2O. So 100 minus 24 is 76, therefore we have 76 grams of H2O. Now granted, the ratio is what is important. So we can also have 48 grams of HCl, but that will correspond to 200 grams of solution. Or we can have 12 grams of HCl for every 50 grams of solution. But the best way to answer this problem is convert this percentage into grams and base it out of 100. So if you have a 30% HCl solution, that means you have 30 grams of HCl, 70 grams of water, and 100 grams of solution. If you do it that way, then it's going to be easy to get the answer. So now it's going to be similar to the last problem that we did previously, number 32. So let's start with 24 grams of HCl and let's convert it to moles. Chlorine has a molar mass of 35.45, and for hydrogen it's like 1.008. So the molar mass for HCl, it's about 36.458 grams per 1 mole. So these units cancel. And the last thing we need to do is divide by the kilograms of solvent. We have 76 grams of solvent. To convert grams to kilograms, divide by 1,000, or move the decimal 3 units to the left. So 76 grams is equal to 0.076 kilograms. So 24 divided by 36.458, that should give you 0.658 moles, and then divide that by 0.076. So the answer for this problem is 8.66. That's the molality of the solution. So that's how you can convert mass percent into molality. 34. Determine the molarity of a 27% HI solution with a density of 1.21 grams per milliliter. So we know molarity is the moles of solute over the liters of solution. So if we can have the grams of solution, we can use the density to get the milliliters of solution and then the liters of solution, so we can find the molarity. But let's write down what we have. So in a 27% solution, that means that there are 27 grams of HI for every 100 grams of solution. And if we subtract the two numbers, 100 minus 27, that means that we have 73 grams of water. But we probably don't need that for this problem since we're not looking for molality. Now, we can easily get moles of solute by converting grams of HI into moles, but we need the liters of solution. So 100 grams of solution, let's convert that to liters. So the density is 1.21 grams per milliliter. That means that 1 milliliter of solution has about 1.21 grams. So notice that the grams cancel. And now we can convert milliliters into liters. There's 1,000 milliliters per 1 liter. So 100 divided by 1.21 divided by 1,000, we have a volume of 0.0826 liters. So now we can calculate the molarity. So starting with 27 grams of HI, let's convert it to moles. Iodine has a molar mass of 126.9 plus 1.008 for hydrogen, so the molar mass is 127.908. Now that we have moles of solute on top, all we need to do is divide it by the liters of solution to get molarity. So 27 divided by 127.908, you should get 0.211, and then divide that by 0.0826, and the final answer is about 2.55. So answer choice C is the right answer. It really rounds to 2.56, but C is the closest answer. Number 35. Determine the boiling point of an aqueous solution of aluminum chloride. So in this problem, we have the molality, we have the Kb. The equation that we need is the temperature of the solution minus the temperature of the solvent is equal to Kb times the molality times the Van Hoff factor. You might have seen this equation as delta T equals Kb times M times I. Just keep in mind that delta T is the temperature difference between the boiling point of the solution and the boiling point of pure water. Now, the only thing that we need in this equation is the Van Hoff factor. What is the Van Hoff factor for this problem? Well, look at aluminum chloride. How many ions can aluminum chloride dissociate into? Aluminum chloride contains an aluminum plus 3 ion and 3 chloride ions. So it has a total of 4 ions. So therefore, the Van Hoff factor is 4. 1 mole of aluminum chloride will generate 4 moles of ions. So now if we plug in the numbers that we have in this equation, this is what we'll have. The temperature of the solution minus the temperature of pure water, which is the boiling point of pure water is 100 degrees Celsius. Kb, that's 0.512. The molality is 1.24. And the Van Hoff factor is 4. So now we have to solve for the boiling point of the solution. So 0.512 times 1.24 times 4 will give us a value of 2.5395. So now we just have to add 100 to both sides. So the boiling point is going to be 102.5 if you add 100 to 2.5. So answer choice C is the right answer. So keep in mind, whenever you add salt to water, the boiling point goes up. So let's say if you have pure water, which has a boiling point of 100. Once you add salt to it, the boiling point could increase to like maybe 102. The freezing point of pure water is about 0 degrees Celsius. And if you add salt to that, the freezing point goes down. It could be like maybe -5 or -10, depending on how much you add. So the equation that we dealt with is called boiling point elevation, because anytime you add salt to water, the boiling point goes up. And there's another equation which is very similar. It's delta Tf is equal to negative Kf m times I. This is called freezing point depression, because when you add salt to water, the freezing point or melting point decreases. It becomes less than 0. And this is why salt is added to icy roads, because whenever you add salt to ice, the melting point of ice decreases, and so it's easy for ice to melt whenever salt is added to it. So those are some things that you want to keep in mind as relates to this topic. Number 36. 32 grams of an unknown non-electrolyte solute was dissolved in 345 milliliters of solution. The osmotic pressure of the resulting solution is 27.1 atmospheres at 298 Kelvin. Calculate the molar mass of the unknown solute. So the important expression that we have is osmotic pressure. Pi, which is osmotic pressure, is equal to the molarity times the gas constant times the temperature times the Van Hoff factor. Now, in order to find the molar mass, we need the grams, and we need to divide that by the moles. Now, we already have the grams. It's 32 grams. That's the grams of the solute. In order to find moles, we've got to find molarity. So we can rewrite the equation like this. Pi is equal to moles over liters times RT times I. So our goal is to solve for the moles. So let's plug in what we have. The pressure is pi, which is 27.1. And for the moles, we're going to call it X. That's what we're looking for. Now the liters is the volume. We have 345 milliliters of solution. To convert that into liters, we've got to divide that by 1,000. So that's equal to 0.345 liters. And then R is the gas constant. That's 0.08206. The other one, 8.3145, that has units joules per mole Kelvin, but we need to use this one because it has the units ATM in it, and it has liters as well. The temperature is 298 Kelvin, and the Van Hoff factor for a non-electrolyte is always equal to 1 because non-electrolytes do not dissociate into ions. So now we need to do math to solve for X. So let's multiply both sides by 0.345. So these numbers will cancel. So on the left, if we multiply 27.1 times 0.345, we should get 9.3495. And that's equal to 298 times 0.08206. So that's going to give us 24.45388x. So if we divide both sides by 24.45388, x is equal to 0.3823 moles. Now, in order to find the molar mass, we need to take the grams, which is 32 grams, and divide it by the number of moles. And so we get 83.7 grams per mole. And that's it. So D is the right answer. Number 37. 35.1 grams of sodium chloride is dissolved in 200 grams of water. The vapor pressure of pure water is 23.76 torr at 25 degrees Celsius. Calculate the vapor pressure of the solution. The equation that you need for this problem is the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. Now, we already have the vapor pressure of the solvent. For pure water, it's 23.76. But what we need is to find the mole fraction of the solvent. So let's convert everything into moles. So we have 35.1 grams of sodium chloride. And the molar mass for NaCl, for Na it's about 23, and for chlorine it's about 35.45. So that gives us a molar mass of 58.45 grams. Now, we need to take into account that sodium chloride has a Van Hoff factor of 2. That means there's 2 ions per formula unit. And since vapor pressure is a colligative property, which is a property that is dependent on the number of solute particles, we have to find the moles of ions rather than the moles of sodium chloride. So there's 2 moles of ions per 1 mole of NaCl. So we have to multiply the moles of NaCl by 2. So 35.1 divided by 58.45 multiplied by 2. You should get 1.2 moles of ions. Now, let's convert the 200 grams of water into moles. Water has a molar mass of about 18.02 grams per mole. So for water, we have 11.1 moles of H2O. So now we can find the mole fraction of the solvent, which is the mole fraction of water. The mole fraction of water is the moles of water, which is 11.1, divided by the total moles, which is the moles of water plus the moles of the solute particles. So the mole fraction that you should get for water is about 0.902. So now we can use this equation. So the vapor pressure of the solution is equal to the mole fraction of water, which is the solvent, times the vapor pressure of the solvent, which is 23.76 torr. So the answer that you should get is 21.43 torr. So answer choice B is the correct answer for this problem. Number 38. Calculate the average atomic mass of boron if the relative percent abundance of isotopes B10 and B11 are 19% and 81% respectively. So what we need to do is we need to take a weighted average of the mass of the isotopes. So the equation that you need looks something like this. So the weighted average is equal to the first mass times the percentage that corresponds to that mass plus the second mass times its respective percentage. So the first mass, isotope 10, or B10, has a mass of 10, and the percentage for that is about 19%, which as a decimal, that's 0.19. You just divide 19 by 100. Now the second mass, B11, has an atomic mass of 11, and 81% as a decimal is 0.81. So at this point, all you need to do is really you just got to type it in the calculator. So you should get, for your final answer, 10.81. So that's the average atomic mass of boron. So B is the answer. Number 39, 15.5 grams of magnesium metal reacts with excess nitrogen gas to produce 18.2 grams of magnesium nitride. Calculate the percent yield of magnesium nitride. So the first thing we need to do is write a balanced reaction. So magnesium is Mg, and it's going to react with nitrogen gas, which is N2, it's diatomic, and that's going to produce magnesium nitride. So magnesium nitride is an ionic compound, so we can't just write MgN. You have to make sure you write it in the correct ratio. Magnesium is in group 2, so as an ion, it has a +2 charge. And nitrogen is in group like 15 or 5A, and it has a minus charge, a -3 charge. So you got to use like this crisscross method where the 2 is going to go here, the 3 is going to go there. And so the correct formula is Mg3N2. So now we need to balance the reaction. We have 2 nitrogen atoms on both sides, so we don't have to worry about that. All we need to do is put a 3 in front of Mg. So it's 3, 1, 1. So now this problem wants us to find the percent yield. The equation for percent yield, it's equal to actual yield divided by theoretical yield times 100%. Now usually the actual yield is given to you if you need to find the percent yield. And the yield is based on a product. So notice that they mention, or this problem mentioned that 18.2 grams of magnesium nitride was produced. So that's the actual yield for this particular reaction. So we got to find the theoretical yield. The theoretical yield is the maximum amount of mass, or grams, it could be in moles too, the maximum amount of product that can be produced in a reaction. So we know nitrogen gas is the excess reactant. That means magnesium metal is the limiting reactant. So let's go ahead and solve this problem. So we need to convert grams of magnesium to grams of magnesium nitride, and that's going to be the theoretical yield. So let's start with 15.5 grams of magnesium, and let's convert it to moles. In order to convert it to moles, we need to use the molar mass. For magnesium, it's about 24.31 grams. So the units grams cancel. So now we can convert moles of magnesium to moles of magnesium nitride. So we need to use the molar ratio. It's a 3-to-1 ratio. So for every 1 mole of magnesium nitride that's produced in a reaction, 3 moles of magnesium are consumed. The last step is to convert magnesium nitride from moles to grams. So we need to find the molar mass. So we have 3 magnesium atoms, so it's going to be 3 times 24.31, and 2 nitrogen atoms, which is 2 times 14.01. And I'm going to use the calculator for this. If I did that correctly, that is equal to 100.95. So it's 100.95 grams per 1 mole of magnesium nitride. So moles of Mg cancel, and moles of MgN3 cancel. So now we have the grams. So to calculate it, it's going to be 15.5 divided by 24.31. Take that result and then divide it by 3 and then multiply it by 100.95. If you did it correctly, you should get this answer. This is the theoretical yield of the product. So that's the maximum amount of magnesium nitride that we can get if all of the 15.5 grams of magnesium metal reacts. That's the most that we can produce in this reaction. But now, according to this problem, we only got 18.2 grams of magnesium nitride out of the maximum 21.455 grams. So this is how you calculate percent yield. It's going to be the actual yield, which I'm going to represent as AY, divided by the theoretical yield, and then times 100%. So if you plug those numbers in, the answer should be 84.8%. So that's the answer to the problem. So answer choice C is the correct answer for this problem. Number 40. Calculate the pH of a 5.43 times 10 to the minus 3 mole solution of barium hydroxide. The first thing we need to do is find the concentration of hydroxide. If we can do that, we can find the pOH and then we can find the pH of the solution. So barium hydroxide dissociates into the barium plus 2 ion and 2 hydroxide ions in water. Barium hydroxide is fairly soluble in water. And so notice that we have a 1 to 2 ratio between barium hydroxide and the hydroxide ions. So if you wish to find the concentration of hydroxide, we need to multiply the concentration of barium hydroxide by 2 because we have a 1 to 2 ratio. But if you wish to convert it, you can write it like this: 5.43 times 10 to the minus 3 for barium hydroxide, and then you can multiply it by the 2 to 1 ratio. So therefore, the concentration of hydroxide is about 0.01086 m. So now we can find the pOH, which is negative log of the hydroxide concentration. So if you type in negative log 0.01086 in your calculator, you should get a pOH value of 1.964. Now another equation that you want to know is that the pH plus the pOH must add to 14 whenever water is a solvent. So therefore, the pH is 14 minus the pOH, or 14 minus 1.964. And that's going to give you the answer. So the pH is equal to 12.04. Answer A is the right answer.